Welcome to the Explainer. Today, we're going to break down the physics behind spherical mirrors. We'll get into all the key terms, the rules that govern how light reflects, and then see how all of this applies to things you and I use every single day. So let's start with something super familiar, something you've probably got in your kitchen right now, a shiny spoon. I mean, have you ever really looked at your reflection in one? Because if you have, you know something pretty weird happens. Look into the inside curve, the part you'd scoop soup with, and bam, your reflection might be completely flipped upside down. But then flip it over to the bulging backside, and suddenly you're right side up again, just smaller. Well, that spoon is actually the perfect introduction to the two main types of spherical mirrors we're going to talk about. Here's our game plan for today. We'll start with the basic parts of a mirror, then we'll dive into the rules of reflection. After that, we'll see how those rules let us predict how an image is formed, and finally, we'll see where all this stuff shows up in the real world. Okay, first things first. Before we can start predicting what a reflection is going to look like, we need to learn the language. We've got to get familiar with the basic anatomy that scientists use to talk about these mirrors. So, back to our spoon. The two sides are perfect examples of the two types of spherical mirrors. The side that curves inward, that's a concave mirror. A good way to remember it is that it goes in, like a cave. The other side, the one that bulges out, that's a convex mirror. Every spherical mirror has a point that's smack dab in the geometric center of its surface. We call that the pole, and we usually label it with a P. Just think of it as our starting point, our zero on the map of the mirror. Now, I want you to imagine that our mirror is just a small piece that's been sliced off a much larger, perfectly round sphere. The center of that original, big sphere is what we call the center of curvature, or C. It's a super important reference point that sits out in front of a concave mirror or behind a convex one. All right, now for a really key concept, the principal focus, or just F. For a concave mirror, this is the magic spot where parallel rays of light all meet up after they bounce off the mirror's surface. It's a real point of concentrated energy. In fact, our source material even mentions that if you point a concave mirror at the sun, this focal point gets so hot it can literally burn paper. So these 3 points we've just defined, the pole, the center of curvature, and the focus, they're not just randomly placed. They share a very precise, very simple mathematical relationship. If you know where one is, you can always figure out the others. And here it is. It's this simple. R equals 2F. All that means is that the radius of curvature, which is the distance from the mirror's pole P out to the center of curvature C, is always exactly double the focal length, which is the distance from P to the focus F. So, bottom line, the focus, F, is always sitting perfectly in the middle, right between the mirror's surface and its center of curvature. All right, we've got the anatomy down. Now let's learn the rules of the road for light rays. Think of these 4 predictable paths as our toolkit. They're all we need to figure out exactly where an image is going to form and what it's going to look like. So here they are, the 4 predictable paths. Rule 1, a light ray coming in parallel to the main axis always reflects through the focal point, F. Rule 2, the reverse is also true. A ray that passes through F first will bounce off and travel out parallel. Rule 3, a ray that goes through the center of curvature, C, hits the mirror and bounces straight back along the same path. And Rule 4, a ray that hits the mirror right at the pole reflects off at the exact same angle it came in at. Now here's the best part. You only need to draw 2 of these rays from any object to find the exact point where its reflection will appear. Okay, we have our toolkit of rules. Let's put on our image detective hats and actually put this theory into practice. We can now predict exactly what we're going to see based on where we place an object. Let's run a little experiment in our minds. Imagine we have a small candle. What happens to its reflection as we move it closer and closer to a concave mirror? Let's start with it really far away and just see how the image changes as we bring it in. This table lays it all out for us perfectly. Just follow that first column. As our candle moves from way out at infinity and gets closer and closer to the mirror, watch what happens to the image. The reflection starts out as real and inverted, and it actually moves away from the mirror, getting bigger and bigger as it goes. It starts out tiny, then it's the same size, and then it becomes enlarged, right up until we cross that focal point. Now, check out that last row. This is the game changer. The moment our candle moves inside the focal length, in that space between the mirror and point F, the rules totally change. The image flips, so it's upright or erect, it's enlarged, and it looks like it's behind the mirror. This is what we call a virtual image. And this right here is the exact principle that makes shaving mirrors or makeup mirrors work. So why does all this matter outside of a science class? Well, because these principles are absolutely everywhere. Let's take a look at how they show up in technology we use all the time. You know that rule about light coming from the focus and reflecting out in a parallel beam? That's exactly how flashlights and car headlights are designed. The little bulb is placed right at the focal point to create a strong, focused beam. We already talked about makeup mirrors, but solar furnaces use the opposite idea. They use giant concave mirrors to take all the parallel rays from the sun and concentrate them onto a single, intensely hot spot. Okay, time to flip the spoon back over. Why are the side mirrors on cars, the ones that often have that little warning, objects in mirror are closer than they appear, why are they always convex?
The answer is all about safety, and it comes down to two big things. First, unlike a concave mirror, a convex mirror always gives you an upright image. You definitely don't want to see cars behind you flipped upside down. And second, by making the reflected image smaller, the mirror is able to show you a much, much wider area. It gives the driver a better field of view, and that's absolutely critical on the road.
This little quote from our source material just sums it up perfectly. A concave mirror's reflection can flip you upside down depending on where you stand, but a convex mirror, or a simple flat mirror, nope, you'll always be upright.
So by understanding these simple rules, you really start to see this kind of physics hiding in plain sight. From the big security mirrors in the corner of a store to the shape of a satellite dish, the same rules are at play. So now that you know what to look for, what other spherical mirrors can you spot in the world around you?